starting? So I have your test to give back, but I'll give those back at the end of class. So I'm just going to jump into it and continue to move forward. So I believe where we are is in 4.2, where we're talking about subspaces. So let's recall, because we know that subspaces are subsets of vector spaces that are also vector spaces, so let's recall what is a vector space. This is a non-empty set of objects, and they can be very general, so vectors doesn't have to be all vectors with two operations defined. This is which we call addition, but that's in quotations because addition can take on multiple meanings depending on context, and scalar multiplication. That fulfill 10 axioms. Right? So I'm not going to relist those. These are the familiar axioms basically that work on the calculus 3 vectors if we ignore all vector products. But addition is just some sort of mechanism to combine two vectors to get another vector. Alright, so any rule that we have to do with that, where I can take two vectors and through some rule that obeys the 10 axioms, I combine them in such a way to get another vector, I call that addition. And scalar multiplication combines a scalar and a vector to obtain another vector. So that was what a vector space was. And so, yeah, as the 10 axioms are basically the algebraic properties of the vectors that you're familiar with from calculus 3. So if you add two vectors, you get another vector. There's a zero vector. Each vector has a negative. Addition is commutative. It's associative. And 1 times the vector is the vector itself, and so on and so forth. And you have distributive properties and etc. Okay, so that was a vector space. Now, a subspace is a subset of a vector space that is itself a vector space. So when you have a vector space, a set of objects with these two operations defined on it, sometimes you can take a smaller subgroup of that, a subspace of that, and that group by itself will obey all these 10 axioms as well. And we looked at a theorem of how we can know that something is a subspace. So let V be a vector space, and U is a subset of V, then U is a subspace if and only if. What were the conditions that made a subset a subspace? Yeah?
Closed under addition.
One was closed under addition. Meaning if every time you add two elements to this anytime you add two vectors, you get another vector that stays in this subset. So for example, I can take the set of integers as a vector space over the scalar of integers. And if I take a subset of that to be the odd integers, it turns out that is not a subspace. Because if I add two odd integers, I get an even integer and I exit the group. Whereas if I take the subset of the even integers, that is a subspace. And 2, it's closed under scalar multiplications. And again, one thing that you want to be tempted, you might be tempted to think of addition and scalar multiplication in the conventional sense, but it's not always that, so you have to really pay attention to the context. It's just saying, if I take two elements in the subset and I combine them using whatever rule you give me for combining two vectors and getting another vector, I will obtain an answer whose properties satisfy elements of U. And I think that's pretty much where we stopped off. Did we give any examples of subspaces yet?
No.
So let's actually do some examples. So that's just to bring you up to speed where we were. We did that theorem, and I believe we proved that theorem. And so now let's look at some examples. And especially when you're exploring a new idea, it's often useful to look at non-examples as well. Something that might almost seem like it, but it's not quite it. There are some very important examples. For example, one is called the zero subspace. So this is a very trivial subspace. It's literally a set that only contains one element, that element being the zero vector. So it's called the zero subspace. So that is, i.e., V is the set that only contains the zero vector, where of course 0 plus 0 equals 0. And if I take a scalar times 0, I get 0. So the output is always going to be 0, the input is always going to be 0, and so there's really, it doesn't go anywhere, but it does fulfill all the 10 axioms of a vector space, and so it is a vector space. And this is in fact a subspace of any vector space. Right? Because every vector space contains a zero vector. So you can always look inside that and just pick out the zero vector by itself, and you've created a subspace. This would be the smallest subspace possible, yeah?
If it doesn't have a zero space, then it's not a vector.
If it does not have a zero vector, it's not a vector space in the beginning. Yeah, that's correct. Having an element that functions as 0 is one of the axioms. I don't remember what number it is, probably axiom 4 or something like that. But it's a defining quality of a vector space is the presence of a zero vector. So if you just look at the set of the zero vector, that is automatically a subspace of any vector space. Right? The 0 here can mean anything. Depends on the context. So if we're looking at a set of 2 by 2 matrices, this is just this 0, 0, 0, 0. If we're looking in R2, this is just the vector with the component 0, 0, and so on. So this can take on a multitude of meanings depending on the context. But in whatever context you're looking in, we just take out the 0 vector from that context and put it in a set by itself that is a subspace of the original space. So that's a very important set.
Question.
Yes?
How did you, oh, well, you can apply the same concept with the vector space and use the same exercise, or the same example. How do you distinguish when is a vector space and when is a vector subspace?
Again, it all depends on context. So it depends on what you're interested in. At any given time, you'll know what it is you're studying. So you can say, okay, I'm looking at R3, right? But let's look at a subspace of R3. So you know you're looking at something that's not the whole 3 space, but it's just a part of 3 space, right? So you'll consider, okay, R3 is the universe, that's everything, that's my vector space. What components of this can I study as vector spaces themselves? And it turns out in R3, if I take the 0 vector, which is just like 0, 0, so this depends on context. So if I'm in R3, my 0 would just be the component of 3 zeros. If I'm in the set of 2 by 2 matrices, my 0 vector will take on this form. Yes?
I thought like vector 0 is just a starting point of vector. Like, it could be like anywhere instead of middle point, you know what I mean?
No. The 0 vector is a vector such that if I add it to any vector in the vector space, the result is the vector itself. The whole magnitude and direction interpretation does not apply in linear algebra. Right, so in R3, that would be the 0. If I'm looking at the set of 2 by 2 matrices, this would be my 0. If I'm looking at the set of polynomials of degree n or less, then my 0 vector is actually the 0 number that's in the real numbers, and so on and so forth. So 0 can mean a multitude of things, depending on the context you're looking at.
Can be a function?
Hmm?
Can be used as a function?
Yeah, for example, the set of polynomials, these are sets of functions. And so it can vary. But that's a very important subspace. By the way, this is just something we can say in passing. If V is a vector space, it is a subspace of itself. It's kind of one of those weird things. The set is also a subset. Every set is a subset of itself. So that's automatic. Often not useful, but it's actually mathematically speaking true to say that. Another one. So I already picked out some nice examples, so let's look at those. So let's look at, here's an example. We know, or we should know, the set of matrices actually form a vector space. So if you look at matrices of a certain size, take all matrices of a certain size, they will form a vector space. They will fulfill all the 10 axioms. So we know the set of, set of n by m matrices is a vector space. So let's look at some subspaces of that. For example, the set of symmetric matrices in this vector space is subspace or not? What do you think?
Yeah.
Hmm?
Yeah.
It is a vector space. Right? And you can prove that using the two. I mean, I'm not going to do this for every example, but just to, you know, spring break has been a long time. I'm going to forget a lot, so let's just prove a couple things while we're moving on. So let U equals a set of symmetric matrices in the set of n by m matrices, and so let A and B be elements of U, i.e., what does it mean to be symmetric? It's equal to its transpose, and B is equal to its transpose. And so now when you look at the sum, A plus B, right? That we know A is equal to its transpose, B is equal to its transpose. There's a property of transpose that says transposition distributes across sums. And so this means that A plus B is an element of U as well. So if two individual matrices are symmetric, their sum is symmetric. So this gives you closure under addition. And we also know that if K times A, this is, if I take the transpose of that, this is K times A transpose. But A is a symmetric matrix, so A transpose is equal to A. So constant isomatric transpose is itself, which means that Ka is also in U, and that gives us closure under scalar multiplication. And once I check those things, it means it's a subspace. Now, one thing I want to get, it's a very short example, but I want to make sure you get the idea here. There's a very important idea expressed here. What you have to show is that the properties of each individual vector in the set is satisfied by sums of vectors in the sets, and it's satisfied by scalar multiples of vectors in the set. So there will be some defining quality of your set. You say, this is the set of all things that have this property. You need to show that the sum has that specific property. You also need to show that the scalar multiple has that specific property. So when it comes to showing closure under addition and scalar multiplication, you're basically showing that if I add two vectors, they will have the same property as the individuals have. And if I multiply a vector by a scalar, it will have the same property that individuals have. Those are the two things that you have to check. So the set of matrices of a certain size is a vector space. It fulfills the 10 axioms. If I extract from that set the set of matrices that are symmetric, clearly the zero vector is also in this set, so it automatically has the zero vector. That will actually form a subspace. Here's an example. The set of invertible matrices in B equals, let's look at the square matrices, the n by n matrices. And I'm going to extract the invertible matrices. Is or is not a subspace? What do you guys think? Subspace? You say no, why? Right, it's not a subspace. It's an easy thing to check. You take a matrix that has a non-zero determinant, say A with determinant of A not equal to 0. Then if we take the negative of A, we'll also have determinant not 0. Right? But then if I take A and I add it to negative A, I would get the 0 vector, which is not invertible. Right? So I add two invertible matrices, the result is not an invertible matrix. So it's not closed under addition, and so this does not form a subspace. I cannot treat the set of invertible matrices as a vector space in its own right. And there was a question on this, similar on the first test, where I asked you, Provided you can actually add A and B. If you know that A inverse exists and B inverse exists, does A minus B inverse exist? And the answer was no. And you could just come up with an example similar to this. Right? Just take A equals 1, 2, 3, 4. We know that has non-zero determinant, so it has an inverse. But take B equals A. Then the subtraction would give you the 0 vector. It doesn't have an inverse because the determinant is 0. So this would mean that A minus B would be equal to the 0 vector, which in this case is the 2 by 2 0 matrix. And so A minus B inverse does not exist. So for that problem in the first test, it didn't have an inverse. So it could not form a subspace, in other words. Right? It's also easy to see because even scalar multiplication doesn't work, because you could also say that A is invertible, but if the subset is closed under scalar multiplication, I can take 0 times A, but that will give me the 0 vector, because there's a theorem that says if I multiply the 0 scalar by a vector, it gives me the 0 vector, is not invertible. So it's neither closed under scalar multiplication. So the invertible matrices do not behave as a vector space. So that's a non-example. Symmetric matrices, they will behave like vector spaces. They will obey all the 10 axioms of vector spaces, but this is not true for invertible matrices. What's another set of matrices? What about square matrices? The set of square matrices. So I look at the space of all matrices of finite size, and I pick out only the square ones.
Yes.
So let's look at, say, the set of 2 by 2 matrices. Right? Square matrices of a certain size. This is a subspace. Why? Because if I add two 2 by 2 matrices, the result is a 2 by 2, and if I multiply a 2 by 2 by a scalar, the result is a 2 by 2. It's closed under addition and scalar multiplication, so it is a subspace. Other examples. Okay, so let R2 be my vector space. Equipped with two operations, which is the typical vector addition and scalar multiplication that you learned from Calc 3. And so let U equals the set of all vectors in R2 such that it has this form. Do the set of all such vectors form a vector space? So in other words, what I'm asking, in R2, do the set of all points on the parabola if I look at all these vectors, that gives me coordinates along a parabola. Right, so that's one vector, that's another 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 vector. Look at all these possible vectors. If I group all those vectors in a set on their own, do they form a vector space? Yeah?
No.
How would you know?
Because scalar multiplication would not preserve it?
Scalar multiplication, so give me an example.
Like, if you had a particular vector in that direction, and you multiplied it by -1, it would be in the opposite quadrant, and that wouldn't work.
Right, so let a comma a squared plus 1 be an element of U. If I take -1 times this guy, this would be equal to minus a comma minus a squared minus 1. Now notice, what would it have to look like in order to be? Let's pretend for a little while. What would this have to look like in order for me to say, yes, it is a subspace?
The inverse of.
To be a subspace, we had to, so the answer is here, it's not. We had to have gotten, so the rule is, whatever you have in the first component, you square it and you add 1. So it means if my first component was a minus a, the second component should be minus a squared plus 1. Clearly, that is not the case. The answer that I got does not look like this property. It does not have this property. It is not true that the second component is the square of the first component plus 1. Right? There's a property that that a vector has to have to belong to this set, but a scalar multiple of the vector does not have that property. So I can say it's not closed under scalar multiplication. It's also easy to see that it's not closed under addition, right? So if I take two such vectors and I add them together, I would not get such a vector. Right?
Professor,
Yes.
if you did a and a cubed, that would be a vector space.
Well, hold on, just give me a second. So I'll deal with that right after this. Right, I just want you guys to get used to this idea of how you want to approach these things, how you want to look at something. It will always be some defining characteristic that you want to see if you can tweak things to fit that characteristic. In this case, it didn't work with scalar multiplication, but let's say on a quiz or a test or in your homework, you actually tried to do the addition property first. Would that have worked? In this case, no. So also not closed under addition. Because if, let's say I take two vectors, a squared plus 1, and b comma b squared plus 1, which are elements of U, if I take this guy and I added it to that guy, under the usual addition, I would get a plus b, comma, here I'd have a squared plus b squared plus 2. In particular, this is not equal to a plus b all squared plus 1. Right? The second component does not fit with what it should look like. Right? It is not the square of the first component plus 1. It's something else entirely. Right? So it's not closed under addition either. There are situations where it's closed under one of these but not the other, so you do have to check both, right? But once one of them fail, you can automatically stop because it's not a vector space. But if one of these works, you need to check the other one to make sure. You said,
Well,
you said
If it was cubed?
if it was the set of things that look like a comma a cubed.
yeah,
So now you're looking at the set of things that points that form along.
yeah, but it doesn't, it's not closed under scalar multiplication.
Right, it's not.
Yeah. But,
And it's not closed under addition either.
right.
Yeah.
But can you jump in a case like this where it's an equation, where it's like a vector that's based on an equation? Can you jump straight to saying that there's no, like if you just know there's no zero vector, can you jump straight to that?
Yeah, yeah. So I can automatically see here, with the first example where it was a squared plus 1, you could also say oh, I know the 0 vector of the vector space is the component with 0, 0.
Right.
But such a coordinate wouldn't exist with this rule, so it doesn't have a 0 vector. Yeah. So I don't remember if I mentioned that, but if something is not a subspace, it's usually one of these 3 things that will fail. You usually don't have to go through the list of 10 things. It'll either be like the 0 vector is missing, or if I add 2 things, I don't get something, or if I multiply by a scalar, I don't get the right thing. But these are the main things you want to look for. And if there's something that you know is a vector space, like you verified all 10 rules for a certain set, then if you take a subset of that set, you only have to verify 2 rules to know whether that subset is a vector space, namely these 2. So let's actually capitalize on this example because it was another example. Let's talk about the subspaces of Rn. Now this would be easier with some theory that we're going to do down the road, but let's actually just discuss this now. Let's take, let's look at these guys. And here, it turns out there are actually not that many when you look at all the categories. Possible subspaces. So R versus R2 versus, let's look at Rn. So what are possible subspaces of R? Let's say I took all the real numbers over the real numbers. I think of them as a vector space with all the real number properties. I know the real numbers form a vector space, but let's look at the possible subspaces of real numbers. What subset of real numbers will form a vector space?
Any suggestion, or does it have to be right?
Well, yeah. Well, any suggestion would be helpful. We can talk about it.
Integers?
No, this here, this is a vector space over itself, over R. So R also contains my scalars. So the integers wouldn't work because you multiply an integer by a real number, you might not get an integer. So no, the integers would not form a subspace. Start with the easier ones. There are 2 that are 0. If I look at the set that only contains the real number 0, that is a subspace. What's another one? The space itself is a subspace. What is another one?
Rational numbers?
No?
No, because
Because if I multiply by a rational by a real number, it doesn't work. Turns out in R, those are the only 2 possible subspaces. Right? Which I know it's kind of anticlimactic, but yeah, R is like that. Let's go with R2. And again, here the 0 vector will work, right? That's just the vector with 2 component zeros. The space itself would work. What else would work? Is there anything else that would work? So we already saw examples like a parabola would not work, right? Because if I add 2 components, the sum of a square is not the square of the sums. So that won't work. So parabola is not going to work. What kind of things could possibly work here?
a line.
A line might work. Can any line work? Let's say I look at the line x plus 1.
No, it has to be the original.
Would that work? Because I could express such components as a comma a plus 1. Now if I add 2 things that look like that, I would get a plus b comma a plus b plus 2. It wouldn't look like this, right? Also, how would I get the 0 vector here? I can't. In order to get the 0 vector, the first component needs to be 0, so I'd have to plug in 0 for a, but then 1 would be in the second coordinate. So this does not include the 0 vector, so it's automatically not a vector space. It turns out that in order to get a vector space, it has to be a line through the origin. So it can't just be any line. It has to pass through the origin, right? If you go up to R3, possible vector spaces are 0, and remember in this case 0 is 0, 0, 0. The space itself is a subspace. Lines through the origin, right, for the same reason. Anyone else? Planes through the origin. So if you look at all planes that pass through the origin, that set of things is a vector space. It actually forms a subspace of R3. And this actually generalizes. So for Rn, the zero vector containing is always a subspace. The set itself is always a subspace. Lines through origin will always be subspace. And planes through origin will always be subspace. Notice here though, once you get higher than 3 space, you can have hyperplanes. So you can have a 2D plane, a 3D plane, a 4D plane, and so on. So the bigger your n is, the more multi-dimensional planes you can have, but every subspace has to be a plane.
Up to n minus 1.
Up to n minus 1. So those are the only subspaces. Right, yeah.
Is it not though up to n? Because, I mean, the plane to the origin R2 is R2.
Plane to the origin in R2.
These R2.
Yeah, but that fits over here. So when you go up to the n case, it's this. It's a
Right,
set.
I mean, but it is up to n.
I mean, technically it's up to n. Once you hit n, you're actually everyone. Yeah.
What about like her hyperboloid, but
Right, which, by the way, this kind of, to just mention something here, like when we were doing calculus up to this point, these were the spaces we were usually working in, right? When you went up to Calc 3, you stopped working here, but you could have gone further. And it just so turns out, when you look at the subsets of these guys that will fulfill all the algebraic properties that you're used to and that work out nicely, it turns out that these are all linear. Hence the study of linear algebra, right? When you go into calculus and you kind of want to extract from it all the really, really nice things, the things that really behave in such a way that you can sort of close your eyes and know what's going to happen, it turns out that they're always going to be linear. Yeah.
what about like a paraboloid that goes to the origin for Rn?
It's not going to work for the same reason that the parabola didn't work here in R2. Because when I add the formulas for 2 paraboloids, the sum of that would not be the same kind of paraboloid. It would be like a paraboloid that's outside the set.
There wouldn't be any closure for addition and
Yeah,
scalar
there will
multiplication.
be neither. So it turns out we have to be linear in order to maintain the vector space property, and moreover, we have to contain the 0 vector. So it forces us to be linear and pass through the origin. So all n-dimensional things that pass through the origin in Rn, all linear, n-linear things will be the vector spaces. So when you're looking at R2, for example, there are only 3 possible types of vector spaces. Anything that does not fall into one of these 3 categories is not a vector space. So you can automatically know if someone's talking about, let's look at the set of all cubic functions in R2, not a vector space. Linear algebra does not apply, right? That's calculus.
What about trigonometric functions? Those wouldn't apply either.
Don't apply, right?
Just linear function.
Yeah, because the sine of A plus the sine of B is not the sine of A plus B, right? There's a whole formula that you have to go through. Right, so if I add 2 things in that set, I don't get a thing that behaves like a thing in that set. So this is one of the things that might spark an interest in studying linear algebra, because when you start to extract things out of these spaces that you're used to working with, the things that really maintain the nice properties tends to be the linear things, right? And these are the guys that we can describe with matrices. Right? And so then we end up with looking at matrices and studying those guys. But yeah, those are some good examples. So I can say, we looked at this last time, and this was the set of continuous functions. Let's see. Set of continuous functions on the real line, right? If I take a subset of that and only look at the, notice that Pn is a subset of this. Right? So look at all the continuous functions. Ignore everyone except the polynomials of degree n or less. Those things form a subspace. I can look at all continuous functions and only extract the ones that have derivatives. The differentiable continuous functions, those also form a subspace, right? Because if I add two differentiable functions, the result is a differentiable function. If I take a scalar multiple of a differentiable function, the result is a differentiable function. In fact, you sort of have this huge picture going on. So I look at the set of all functions, and then inside of that, I can look at the set of all continuous functions. And then the set of all continuous functions that are 1 time differentiable. And the set of all continuous functions that are 2 times differentiable. And so on and so forth. Go all the way down to the set of things that are n times differentiable. And I can look at all the set of things that I can differentiate an infinite number of times. These guys are the guys that we can form Taylor series from. Right? So back in Calc 3, when you talk about a Taylor series, the set of things that you were working with was those guys. Right? Just a small part of the universe. Inside of this is where the Pn would live. Right? Because polynomials happen to be functions you can differentiate infinitely often. So if you look at the set of all polynomials, they're this part of the universe in terms of functions, right? And you can think of functions as living in the set of all relations and things of that sort. So you can get pretty good. Another example. So let A be a coefficient matrix of a system. Ax equals 0. The set of all solutions to this system form a subspace of the domain set. Right? So usually you'll think of these vectors as living in maybe in Rn, right? So if I take all the vectors in Rn that solve that equation, take the set of all those things, I would form a subspace. And we know that this is a homogeneous system. I asked a true or false question about this on the test, right? Such a system is always consistent because x equals the 0 vector will always solve this system. So there's at least one solution, right? But there could be more. There could be one solution or there could be infinitely many solutions, right? But it's always consistent. And if I look at the set of all the possible solutions, they form a vector space. Because 1, if x and y are solutions, that means AX equals 0 and AY equals a 0 vector, then if we consider plugging in the sum of these guys, if you get A of X plus Y, a matrix property says we have the distributive law. But by assumption, this is the 0 vector, that guy's a 0 vector, and that guy gives you 0. So if I have two things that solve this homogeneous system, it turns out their sum will also solve the homogeneous system. So it's closed under addition. Also, if I look at A times K times X, there's a matrix property that says I can factor out the A, the K. And so that just becomes K times 0, and then there's a theorem that tells me a scalar times a 0 vector is the 0 vector. So it's closed under addition and scalar multiplication. So this means it's a subspace. So the solution set here is a subspace. In fact, it's a very important subspace. We actually have a name for it. Definition. The set of solutions to AX equals 0 is called the null space. So we give it a name because it's very important. When we start studying vector spaces, it's going to be a set that's very important to figure out and to find. The set of things that output to 0. It's called a null space. We'll get back to this, but in one of the first 2 lectures when I was talking about looking at matrices as n-dimensional functions where the number of columns tells you the dimension of the input, the number of rows tell you the dimension of the output. So you can kind of think of the matrix as a function. We think of A as a linear transformation. Then a set of X such that AX equals 0 give it another name. It's called the kernel of the linear transformation. It's the same thing like a subspace, it's just in a different context. We call it this name. And it turns out by studying things like the kernel or the null space, it can tell us about the matrix. For example, if your function is a one-to-one function, the solution set to this will be the trivial solution, and that will be the only solution. Right? Any set where we have an infinite number of solutions to this, it will not be a one-to-one function. It will be a linear transformation, but it won't be a one-to-one linear transformation. And there are other things that can arise from this, but we'll talk about that a bit later. So the set of solutions to a homogeneous system actually form a subspace. So that's enough examples for now. Let's actually look at some theorems regarding subspaces and some other vocabulary, and then I'll do some more examples if we have time. Well, this is a theorem, but it kind of gives you other examples as well. So let W1, W2, Wn be vector spaces. same addition and scalar multiplication. Then it turns out, right, so these are all vector spaces. These are groups of things that obey the 10 vector space axioms with respect to some operation. Then if I take the intersection of all of them, which sometimes they might write it as something like this, I goes from 1 up to n of wi, is a subspace. First of all, it's definitely non-empty because everyone will have a zero vector. So there's at least one thing that is in everyone all at the same time. And if that's literally the only thing, that also is a subspace. That's a zero subspace. But even if it has more stuff, that set of things form a subspace. Proof left of the reader. Just when you're too lazy, you just write that. Similar to what some people wrote on the test. There were sometimes I asked them, "Oh, is this?" I forgot the question, but I was asking if something was invertible or something, and just like proved in class, and then they moved on. Sure, but that's not. You can't leave it up to me. I want to know if you. Oh yeah, this was proved in class, and they just move on. Okay. Proof left to you, Javon. You proved it. Come on. Okay. So it turns out the intersection is a subspace. Oh, here's an important definition. Linear combination. I believe I defined this for you before. So let V1 up to Vn be vectors in V, a vector space. Then a linear combination of V1, Vn is an expression C1, V1, these guys are all vectors, plus C2, V2, plus Cn, Vn, where Ci are scalars. Such an expression is called a linear combination. It's a very important kind of expression when it comes to studying objects in linear algebra and vector spaces and how they behave. Note. If we take the set V1 through Vn, and these guys is a subset of V, obviously, because they're just a few vectors that I pick out of V, then W, if I call W the set of all possible linear combinations, is or is not a subspace.
C can be any scalar?
Yeah, C is any scalar. The scalar that corresponds to the vector space I'm studying, yeah. Which in this class, it will usually be the real numbers. So in this class, you can always think of these, the Ci's as real numbers. It is a subspace. clearly, if I take any object that looks like this and I multiply through by a real number, I get another object that looks like this, right? If I take two objects that look like that and I add them together, right? So imagine that I took, so if I look at something like k times c1 v1 plus cn vn, then that is just equal to c1k times v1 plus cnk times vn, right? But that's just going to be a real number as well. That's another linear combination, right? Whereas if I add two linear combinations together, right? If I add like a c1 v1 plus cn vn, and then I add another set of guys like a1 v1 an vn, then if I add them, I just get a1 plus c1 times v1 plus a2 plus c2 times v2 plus an plus cn times vn. The result is another linear combination. So it's closed under scalar multiplication, it's closed under addition. So this forms a subspace. If I look at the set of all possible linear combinations that we can form, it is a subspace. Which means I can look at the set of linear combinations, set of all possible linear combinations, as a vector space. It will fulfill the 10 vector space axioms, and I can use that to get all sorts of nice theorems. W here is it turns out, the smallest. You want to construct the leanest possible subspace of a vector space that contains a few vectors. What you're looking at is the set of all linear combinations of those vectors. So any other subspace of this vector space that contains these vectors will be larger than the set of linear combinations. Larger than or equal to. So W here is the smallest subspace of V that contains these particular vectors. V1 to Vn. So the set of all possible linear combinations is a subspace, and it turns out is the smallest subspace of any vector space that contains the vectors that you care about. What other constructs do we have? And again, there's a proof for that, but that's actually not so bad. Because clearly that we know that's a subspace. I mean, I can just say, we know that it's a subspace. Now think of some other subspace that contains these vectors. Then since it's closed under addition and scalar multiplication, it will automatically contain all objects like this. So it would have to be a set that has inside of it all objects like this. And so it has to be greater than or equal to that object. What else do I want to tell you about? Sorry, I mentioned that. I'll write that down. That might open a can of worms. Definition. E is a vector space. X is an element of V, so X is a vector. And V1 to Vn are also in V. So I take a bunch of vectors, but I'm singling out one of them. If we can write x equals a linear combination of these vectors. There are a bunch of things we can take from that, right? It might not be possible to do this, but suppose we can do this. Then x is said to be in the span of v1 through vn, and the vector, if I look at the vector of coefficients, this is called the coordinates of x. So, example, let my v be R2. Let v1 equals the I vector, v2 equals the j vector, and let x equals the vector, say 1, 3. Then we can write x equals 1 times the I vector plus 3 times the j vector. And I and j are the usual vectors here. This is 1, 0. This is the vector 0, 1. So 1, 3 is the coordinate of x. And in some sense, this function has the location of x with respect to the vectors v1 and v2. I mean, we'll stop there. I mean, before we get to a bunch of examples, I need to tell you a bunch more definitions, so it's not going to be very exciting from here on in. I have to describe a lot more vocabulary to you, and then we'll move on to some more interesting things. Yeah, for now, we're just discovering a lot of new vocabulary and playing around with a lot of new concepts. We'll derive a bunch of stuff later on. And we'll continue next time. For now, I'll give you back here.